Okay, welcome back to another lesson here. Um, so yesterday we had started looking at probability, and I had asked you to try to get an activity done. And I'm actually going to go over that activity with you right now, um, simply because I know some of you may not have had the opportunity to actually get it done, but it's important to see the results, I think, and discuss them a little bit, just so that we can see how this is going to how probability works, basically. So the first part of the activity was to roll a die 10 times and record the result of each roll. And these are the results that I got by doing this. So I just wrote down all the numbers for each time I roll the die over 10 times. And then I tallied them. So this will allow me to show you what I mean by a tally chart a little bit better. These are not ones. These are just what we call tick marks. Tick marks just count up how many times a number has appeared. So the number 1, if you look on my chart, when I rolled the dice, I got 2 ones. So two tick marks, and then the frequency is just the sum of how many of those there are. I got 1, 2, etc., etc. So these are the results that I got from rolling the die 10 times. And I didn't discuss the type of graph to make. I was kind of hoping that you'd be able to figure it out from having seen these kinds of graphs before. When you have a frequency chart like this, you usually use a bar graph to demonstrate how many things we got. What are the totals? So this is the result of the die roll. So how many times did a 1 show up? The frequency tells you how many times. So a 1 showed up twice, 2 showed up once, 3 showed up once, 4 twice, 5 twice, 6 twice. And that should match that frequency table. Okay? Then I asked you to roll the dice another 40 times. Now, I didn't... Oh, sorry. Before that, determine the experimental probability of rolling a 1 after 10 rolls, and write this probability as a fraction, a decimal, and a percent. So your fraction for a probability of rolling a 1, we'd have to go back and look at how many times did we get a 1. Well, we got a 1 twice, and we did 10 rolls. And this is the formula that I showed yesterday. The number of successes of our question and the total number of events or trials, which is 10, because we rolled the die 10 times. So that gives us 2 over 10, and the fraction 2 over 10 can be reduced to 1 over 5. I talked yesterday about the fact that there's usually 3 different ways that we're going to show probability. Fractions are 1, decimals, which is just 1 divided by 5, which gives 0.2, and multiplying 0.2 times 100 gives us our 20%. So right now it's showing a 20% chance of rolling a 1. Okay? And then I had asked you to roll the die another 40 times. Now, I did not write down all of this information. I'm getting this information from a group that I had a couple of years ago, and we had tallied the chart on the board and everything, and I just wrote down the frequencies at the end. So your numbers might be different than mine, but in case you weren't able to do the activity, this is the result of 50 rolls on the die. How many times did we get a 1? 12 times. How many times did we get a 2? 23 times, and these are the results of all of the other ones. This 127 is just the total, okay? So all that is the total amount. We need that total amount to know how many times we actually roll the dice in total, okay? So then I had to place these numbers on the chart, and I realized that I did not give you a properly scaled chart if you were actually going to do this 50 times. So I apologize for that. I just changed my intervals here to go up by 5s so that I'd be able to fit everything in. And this is what the result looks like. Okay, so how many times did a 1 show up? Well, we had said 12, so that's where 12 is approximately. And all of the other heights are, approximately, because we have to guess where they fall between our scales, okay? Now, I don't know if this is a surprising result. There's a lot of bars here that are pretty much the same height. This is the only one that isn't, okay? But when you roll a die, and we'll get back to this a little bit later, you would assume that the probability of each side rolling is the same. Each side of a die is exactly the same shape. The die is supposed to be balanced unless it's a trick dice. You would think that all of these heights would be the same. So it'd be interesting if, we rolled the die 100 times or 1,000 times, what would happen here? And again, we'll discuss that a little later. So then I asked, determine the experimental probability of rolling a 1 after 50 rolls and write this probability as a fraction. Well, if we go back up to our table, we got 12 ones show up out of 127 rolls. So if we do 12 divided by 127, we get 9%. And then I just, at that time, and it's always a good thing to do, you can say how many times did we roll 2s? Well, 2s came up 23 times, which is our number of successes of how many 2s were rolled over our total, which is 127, and that gives 18%. And all of these other values are going to be very close to that. 22, 25, they're all very close to 23. So everything is going to be close to 18%. So the question comes up later on as to what should the probability be. So compare and contrast the two results of the two experimental probabilities. So what's the same? Well, the heights are all very similar. They're not exactly the same, but they are very similar. And for at least one of our die rolls, it was quite lower than all the others. Okay, so that's what's different. Now, your results may have been different than mine. You may have had another height that was a little bit lower, or one of them that was really a little bit higher. But these are the differences and similarities for my numbers. And are the results what you would expect? And this is where I'd like to talk about theoretical probability. Okay, what is the theoretical probability? I'm just going to type this in here. What is the theoretical probability? What is the theoretical probability of rolling a number on a die? Well, this is one of the ways that we often will visualize dice rolls. Okay, and we're going to use these kinds of trees, if you will. These are the branches of the tree here. I know the tree is growing downwards in this case, but just to be able to fit it on the page. So if you have a die, you have each side of the die, and if we look at how many possibilities there are 6 possibilities in all. Each one of these branches is one success out of the total of those trials. So that means that 1 has a 1 in 6 chance of being rolled on a die. 2 has a 1 in 6 chance of being rolled on a die. Each one of these sides has a 1 in 6 chance of being rolled because it's one success out of a total of 6 possibilities. And that gives us 1/6, and 1/6 is 16.6%. So if we go back to what we were getting for our probabilities here, 18% for the majority of them. Now this one was an oddball, but if we had done the rolls 100 or 1,000 times, 9 would get closer and closer to 16, and 18 would also get closer and closer to 16. 18 is pretty close though. So we were already starting to see our theoretical probability after 50 rolls of our dice. So the difference between theoretical probability and experimental probability. Theoretical probability is assuming you tried this 1 billion times what should the results be? And we'll talk about what the theoretical probability of is for certain events later. But for one die roll, just to start talking about this now, it is 1 in 6. Okay? So just to give you a question that you can think about, I don't know how many of you play card games, but cards have an ace to a king, right? So that's 13 faces, or sorry, 13 different types of cards for each type of card. So if it's hearts, you've got 1 to 13 basically, where Jack, Queen, and King is 11, 12, and 13. And there's 4 different suits. Suits is the word I was looking for. There's 4 different suits of cards, right? There's hearts, spades, clubs, and diamonds. So what would be the probability, if I asked you to think about this for later, of pulling a 2 of clubs out of a deck of cards? So that's the kind of thing that we can also discuss when we start to learn more about probabilities. So here's a question out of your textbook. It's on page 62 of your textbook. And it's giving you the table. And from the table, we want to figure out a few answers to certain questions. So it says, how many females would you get? A probability experiment was designed to find the expected number of females in a family of 6 children. To simulate the genders of the 6 children, a coin was tossed 6 times. Heads represented a male, tails represented a female. The experiment was repeated a number of times. So they tossed coins 6 times, but then they did another 6 times, and then another 6 times. Okay? The results are shown in the graph below. So the first question is, how many trials in total were performed? So how would we figure that out? Well, these are the frequencies of how many times we got females in our coin tosses. Okay, so we got no females the first time. Now that means that out of the 6 dice rolls, none of them were females. Okay, so that means all of them were males. In this one here, we got no females. No females. So the frequency of it happening was 0. We got, how many times did we, I'm sorry, I'm messing up here. How many times did we get 1 female out of the 6 dice? Never is what that's saying. Okay, so I was messed up there. How many times did we get 2 females in our rolls? Well, 4 times. How many times did we get 3 females in our rolls? 6 times. How many times did we get 4 females, 5 females, 6 females? Okay, so this frequency chart can tell us how many trials were performed, because all we have to do is add up all of the heights here. Okay, so we've got 1 plus 0 plus 4 plus 6 plus 3, oops, sorry about that, 3 plus 3 plus 0. And that total equals 17. So we know that there were 17 trials done. Each one of these tells us how many females were found in each one of those trials. Okay? So there were 17 in total. What is the experimental probability of having 2 females in a family of 6 children? Well, based on the experimental probability formula, which is number of successes divided by the total, what would be our successes here? Well, having 2 females, the number of females is here. So having 2 females, that happened 4 times. So our number of successes would be 4. Now to write this the proper way, what you do is you write P for probability, and in a bracket you write what we were looking for as our successes. Okay? So I'm going to use a pen to write this down. It's a little bit easier to do a fraction with writing here. So the probability of 2 females, so again, if we look up here, that happened 4 times. So it's 4 out of 17. And using a calculator off screen here, I'm just going to calculate what that percentage is. So 4 divided by 17 is 0.235. As a decimal. And that's rounded. Okay, so the little dot above the equal sign means that it's approximation. And that means that it's 23.5% chance of having 2 females. Then another question that can be asked is, what is the average number of females in a family of 6 children based on the chart? Now, to figure out the average, I'm going to bring in a table here from your textbook. This table shows us another way of organizing the information that was in that chart above. Okay? So if we look at the number of females per family, we know that we had 0 females once. So I'm going to go back up to the table and show you that. We had 0 females once. We had 1 female 0 times. We had 2 females 4 times. So what we have to do is actually multiply those 2 numbers together. 0 females once, 0 times 1 is 0. 1 female 0 times, 1 times 0 is 0. 2 females 4 times, 2 times 4 is 8. So a total of 8 times did that happen. So to calculate an average, we want to add all of these up and divide it by our total number of trials again. So our average is 8 plus, and I hope I don't run out of room here, 18 plus 12 plus 15, because that's our total, and we're going to divide that by the number of trials we had, which was 17, and that gives 53 out of 17, and that gives 3.1 as our average. Okay? So using our table and multiplying our number of females times our occurrences, we figure out the total number of females that we got each time. We add all those up and we divide it by our 17, which was our number of trials, and that gives us our average. So that should be enough information for you to be able to do some of the homework in your textbook. Now, I know some of you may not have the textbook. I'm going to put a link in the Google Classroom so that you can see those questions, okay? And I would like you to work on these as homework for today's lesson. I hope that was pretty easy to follow. I know there might be some questions, especially with that table one. If you do have any questions, try the homework. You can always email me. This is homework. If you want to, if you want to email me a question, a good way to do it is to take a picture and send me the picture through email. Okay. We'll talk to you soon.